now about aromatic compounds. And so now this is a turn from what we've been discussing for the past couple of weeks. So all that carbonyl-chemistry, that was one of our main things that we're going to see. Now we're going to spend a couple days here talking about aromatic compounds. And I'd like to, one, slow down from where we were yesterday. I know we went through that material fast, but also present enough material so that we can let it review over the weekend if you have a chance to do that. So the first thing we want to do is figure out what these aromatic compounds are. And aromatic here doesn't necessarily refer to a good smell. It originally did. Some of the what were defined as aromatic compounds did have a pleasant smell, probably quite toxic. But there's a special definition here for aromatic compounds. And this brings in this idea, as I also put in that video, known as Huckel's rule. And this is a very useful, and we can take a systematic approach to identify aromatic compounds. But when you first see how we do this, it seems really kind of weird or confusing, for lack of a better way. So yes, Lorianne, this is now chapter 17. So what we're doing is we're jumping back in the text. So we put all of this carbonyl chemistry together, and that's why we skipped over 17. Now we're back to 17 for this aromatic chemistry. And I'm just going to lay out here. Yes, thanks for organizing your notes. I don't like going out of order, but I thought hopefully this will work. We'll see. If it's a disaster, just let me know. So we're going to figure out what these compounds are, what defines aromatic, and then relate this to the Huckel's rule. And then this is going to affect, overall, we're really interested in this for the reactivity. We won't get through all of these things maybe today, but this is the main thing. So for the reactivity, we're going to have a major type of reaction, which is known as electrophilic aromatic substitution. Electrophilic aromatic substitution. And here, there's going to be 5 main reactions. But the key thing is to see is it's 5 reactions that have essentially the same mechanism, but a different electrophile. So we're going to use different electrophiles and substitute a hydrogen on the benzene ring as our example here. And then next week, we'll get into something that's known as directing effects. Just want to lay everything out here. And then we have to also cover something that's known as opposed to electrophilic aromatic substitution, there's nucleophilic aromatic substitution. That's the right substitution. Seem to have run out of ink here. Okay, there we go. And then this one, there's 2 main reactions. So that's a bit of a roadmap for how we're going to go forward. And we'll revisit, as I mentioned, a couple of those slides. But let's first go back and revisit this, not really much with nomenclature. I think that was covered a lot in OChem 1, but just to help lay things out again. I'll make my pencil a little bit thicker here. So benzene, we're going to draw it about 100 times between now and next Tuesday, but this will be our baseline aromatic compound. We still have to define what that means. We'll come to that next. So to go through a little bit with the nomenclature, there's a lot of common names that come into these aromatic compounds. I don't want us to memorize these, but just so that we're comfortable using them. Since benzene's the base of many of these compounds, if we have something, say, with a bromine on it, this is bromobenzene. And this works for halogens, alkyl groups, and all sorts of other things. Let's have a propyl group on here. This would be known as propylbenzene. Now, there's many common names that come in to the organic chemistry that are accepted for these aromatic compounds and derivatives of benzene. For example, if we have a methyl group here, technically, then we could call this methylbenzene. But that name is actually rarely used, and instead you see toluene. Now, there's historical reasonings behind all of these different names. I haven't looked them all up on a trusted source like Wikipedia, but we'll just say this is toluene. This is a component in the glue and things like that. If you have a hydroxyl group, could call this hydroxylbenzene, but it's much more commonly known as phenol. You have an ester instead. I'm sorry, I'm smoking ether. There's OCH3. This is anisole. How about an amine? Amine, so rather than aminobenzene, it's typically known as aniline. A couple more. How about a carboxylic acid? We've been seeing those a lot. Rather than calling this some carboxylic acid, it's known as benzoic acid. And this benz name shows up in a few of these common names. But an aldehyde, we're dealing a lot with aldehydes and ketones. This is benzaldehyde. That's an aldehyde. Let's use a ketone here. The ketone, this now name kind of comes out of nowhere, but this is known as acetophenone. And one more. Let's just have an alkene over here. This is known as styrene. So some of them can see a bit of a trend like benzoic acid and benzaldehyde, but there's other names that, again, I don't want us to memorize these, but just so when we're seeing them, we know what phenol means or toluene. And Ryan, you're right. The circle inside the ring is another way of representing the benzene, and we'll show that in a minute. I just like drawing the lines here. It makes it, I guess, it looks messier, I think, this way. But you're welcome to draw the circle inside the ring, and I'll show a plus and minus of that in a minute. Okay, so now more with these common names. Let's think about benzene-related compounds that have more than one substituent on it. So all of these just have either a methyl group or a phenol or so on. So now let's consider di-substituted benzene. So in this case, now we have to think about what groups are shown and what their arrangement is. So let's consider, for example, a compound that has two chloro substituents on it. There's a couple of ways that we can name this. So one, we need to indicate that there's two chlorines and what their relationship is. They could be on the carbons adjacent to each other, right? So we'll call this the 1 and the 2 position, or 1 and 3, or 1 and 4. And actually, let's just draw all three of them to start with. So this arrangement, or this arrangement. And now we can have to think about, we need to somehow indicate that they're both dichloro substituted, but what is that arrangement? So one way of doing this is calling this 1,2-dichloro benzene. And we can do the same thing here, call this 1,3-dichloro benzene. 1,4-dichloro benzene. So that's one way of doing this. But what if you're in a hurry and you want to have a shorter way of saying what the relationship of these two substituents are? There's another convention that we can use. It's actually using this language of ortho-meta-para. And we'll be using this a lot more next week when we start talking about what are known as these directing effects. So if you have a substituent arrangement here that's at the 1 and the 2 position, this is known as ortho. So we could just simply say ortho dichlorobenzene. We're going to run into the other name. Let me erase that. So ortho-dichlorobenzene. Or if that's even too long, we'll just call this O-dichlorobenzene. And if that's the case for the ortho, the 1,2 arrangement, we can do the same thing now for 1,3 and 1,4. And so this 1,3 arrangement will be known as meta. I'll just say dichlorobenzene again, or para. So we're going to be using this language of ortho-meta-para more as we go on. And you're right, James, that when we think about drawing a circle as opposed to the line just representing the resonance hybrid, And we'll get to that in a minute when we talk about the stability. Okay, so we've seen some of our common names. We now come up with some arrangement here of these di-substituted compounds. We've introduced this idea of ortho, meta, para. The two groups do not have to be the same, like what we have here is the two chloros, but we can actually combine some of the common names and this ortho, meta, para. And there's all sorts of variations of this that you could come up with naming complicated compounds. We're only going to consider one or two. So let's imagine we have a compound that looks like this, and I'll just again draw the three lines. This compound now is a hydroxybenzene, if we wanted to think of it that way, but better yet, this is a phenol. So I'll scroll up just a little bit. You can see in our common names, if we have a benzene with the hydroxyl group, that's phenol. So let's use phenol as the parent name, and then call the chloro group here a substituent onto the phenol. So there's two ways we could name this. One is we could call this 4-chlorophenol, or because these groups, it's at the, notice we don't have to put the 1 there because that's the name of phenol, it's in the parent, so that's assumed. So the chloro is at here 1, 2, 3, 4. It doesn't matter if we go around the bottom or the top, that's at the 4 position. However, the other way we could name this is in this 1-4 relationship is that this is para. So we could just simply call this para chlorophenol. Now, this language of ortho, meta, para works, and it's a little bit bigger, if you have 2 substituents, but not if you have 3 substituents or more. So, for example, if we have, looks like we stepped on that benzene ring. Let's just decorate this benzene ring with 3 fluoro substituents. Here. Now, we don't want to have a challenge of saying, oh, the relationship between these 2 fluoros, these are ortho, this fluorine and this fluorine, this is para, these are meta. That gets too complicated too quickly. So here we just need to use the numbers. So we'll call this 1, 2, 4, trifluorobenzene. And one more. We can have, for example, we didn't have this in our earlier common names of compounds. Oh, so nitro we did, but let's call this is toluene, so methylbenzene. And we can put nitro groups on here. We'll see these soon. And so here, we're going to call this toluene. So the methyl group here is going to have the number of 1 for the locant. And so the nitro groups will be at 2, 4, and 6. So this would be 2, 4, 6 trinitro. I didn't save enough space. I'm going to really squeeze it in here. Here, I'll write it larger down below. Two, 4, 6 trinitrotoluene. Or you may have seen this abbreviated as TNT for short. So it's going to be one of our aromatic compounds. All right. So a brief overview of some aspects of nomenclature here. Hopefully some review as we get more comfortable with these structures. We see that there's a systematic way of naming these compounds. However, there's a lot of common names that have crept in the language and are familiar and useful all the time. So you'll see things like toluene, phenol, and so on. We can add substituents. We can describe their arrangement using locants, just like you had seen in OChem 1 for other compounds. But now we have this new language of ortho, meta, para that we're going to be using as well. There's limitations, though, to that. It can only be used when you have these 2 substituents, not if you have multiple substituted benzene rings. And so that's going to be the extent of the nomenclature that we're going to test or discuss. So any comments, questions?